interacting boson model in its version that uses proton bosons and neutron bosons, and we will learn today about new nuclear states that appear when you do this, that are related to the proton-neutron degree of freedom, which is very important in the understanding of nuclei. So again, this lecture was prepared. I received help from Dr. Bella and Dr. Krugman. So let me first motivate this. The nucleus is made of protons and neutrons, so it's a sort of two-fluid system. It's a quantum laboratory for two-fluid systems. It's a many-body system, of course, so it has these two pieces, protons and neutrons, and it's a quantum system, and therefore it's a sort of the best model that we have for these sort of two-fluid quantum systems, many-body quantum system. It shows collectivity. Protons and neutrons have the same underlying forces. The strong forces are isospin independent, so we get this isospin symmetry feature. And because it's a quantum system, finite quantum system, we have this shell structure. And all these aspects are important in what I will discuss today. So the way how these aspects of nuclei coexist and interplay and compete, that will be the topic of this lecture. So if you want to study the competition of these aspects, then you should study collective isovector valence shell excitations. Then you have all these three aspects in, and these states that have this feature are these mixed symmetry states that I will discuss today. So this is the outline. First, I want to introduce the interacting boson model for protons and neutrons. You have heard about the interacting boson model already a lot during this week, in particular the lecture yesterday of Professor Joly, and I think previously by Professor Karsten and Professor van Isacker. Today I want to focus on these mixed symmetry states. I will introduce them, define them, what they are, then discuss the experimental signatures for mixed symmetry states, and the role of experimental observables. Again, I will show a lot of experiments, experimental techniques, and relate them to the theoretical predictions. And then I think I will do a little bit about microscopic description, and give you experimental evidence for the mixed symmetry character. There is very nice review article by one of the organizers, Piet van Isacker, that I can, and others, that I can recommend to read. That was already some time ago, in 1986, but still very nice literature. So you have learned about the interacting boson model. Here we consider the nucleons in a nucleus as paired to in pairs, and they are approximated by bosons, and then you use for a certain nucleus in the nuclear chart the valence particles, so valence protons and valence neutrons, with respect to a nearest doubly magic core. So you use only the valence space dynamics, and you approximate these pairs of protons and pairs of neutrons as neutron and proton bosons. And then you write up a boson Hamiltonian, which consists of boson energies, boson-boson interactions, and in principle higher order terms. In order to keep it simple, usually one neglects higher order terms. And I will discuss mostly only systems where we confine ourselves to monopole bosons and quadrupole bosons, so S and D bosons. In the end, I will maybe discuss a little bit about octupole bosons also. So the for a given nucleus that you consider, you have a fixed number of valence protons and valence neutrons, and that means the number of proton bosons n pi and the number of neutron bosons n nu are separately conserved and constant for a given nucleus. And you have these S and D bosons. They produce, as Professor Joly has discussed yesterday, a U6 structure. So you have one M substate of the S boson, 5 M substates of the D bosons, which is angular momentum 2. In total, 6 M substates, and they form, or they produce such a U6 structure. You have now a U6 structure for the proton bosons, a U6 structure for neutron bosons, and you couple them. That gives a very rich structure, group structure here, and I will discuss one limit of that structure, which is particularly simple. So first takeaway message is the interacting boson model 2 is an interacting boson model for proton bosons and for neutron bosons, in which proton-neutron interactions in the valence shell are treated explicitly. So you can write also the Hamiltonian as a Hamiltonian which contains proton bosons only. That is of the type of interacting boson model 1. So only one type of bosons. So then you can neglect the index of whether it's proton or neutron. So it's just a boson Hamiltonian as it was discussed yesterday. The same for neutrons, like an IBM 1 type Hamiltonian for the neutron bosons. But then there appears also a proton-neutron interaction, which is now a sort of new in this model, and more realistic, if you want. So a simple Hamiltonian that you can consider, out of the many possibilities you can write one boson energy terms and boson-boson interactions, is this Hamiltonian here, which is a sort of pairing plus quadrupole Hamiltonian where you consider also a symmetry energy term. So you recognize some pieces from what you have learned yesterday. So you have the number operator of D bosons now for protons with a proton D boson energy, a number operator of D bosons for neutrons with a neutron D boson energy. You have a quadrupole interaction with some strength. So you can have proton quadrupole times proton quadrupole. You can have neutron quadrupole times neutron quadrupole with some strength. And you can have a proton-neutron quadrupole interaction with another strength constant. And then a term which is called the Majorana interaction, which measures this exchange symmetry of the wave functions with respect to protons and neutrons. I will come to this in more detail later. So here are again a reminder to these operators, the D boson number operators, and D now rho, you can either have protons or neutrons, is just the sum of M substates for the D bosons of that particular isospin rho. So you have D dagger D and sum over all magnetic substates, or you can write it in this scalar product form, D dagger rho dot D tilde, which I hope was introduced. Was the D tilde? Yeah, okay. So these are the D boson number operators that are here, and here are the quadrupole operators, and we have discussed them already in the previous lecture briefly here at the blackboard. So it's for each isospin, it's S dagger D tilde plus D dagger S plus there's an additional term where you have D dagger D coupled to angular momentum 2. Quadrupole is angular momentum 2. And then the Majorana operator, that contains pieces. This is in normal ordering. So here you have two annihilators always a term with protons and neutrons. And here you have the same terms with creation operators. And then D dagger pi, D dagger nu times D pi, D nu coupled to angular momentum k, where k is odd, 1 or 3. These odd tensor products are antisymmetric when you exchange the labels. So when you do d pi d nu coupled to 1, this is minus 1 of d nu d pi coupled to 1. So these are the antisymmetric terms. Also you observe, if you would consider a nucleus with only one type of bosons, let's say only proton bosons, 0 neutron bosons, then this interaction here, because here you always have a neutron boson annihilator present, and they annihilate the vacuum, so that would be 0. So the effect of this operator would be 0 if you have only one type of bosons. And then this Hamiltonian reduces to the ordinary interacting boson model 1. Right? And the value of this symmetry term would be 0 in that case. So this is interesting for the usual case where you have both valence protons and valence neutrons. So when it would reduce to interacting boson model 1, then you get this structure again. You can solve this Hamiltonian, this IBM 1-type Hamiltonian in these 3 dynamical symmetries, U5, SU3, and O6, and depict it again in this sort of symmetry triangle, custom triangle, with these 3 analytical solutions. And you have here the vibrators, here the rigid rotors, and here the gamma soft nuclei. I have discussed in the last lecture, I have discussed this leg here for the deformed nuclei. And there's also a line here which depicts this shape phase transition from spherical nuclei in this region to deformed nuclei in that region. Okay, but now we consider a nucleus that has both valence protons and valence neutrons. Right? That is the topic of this lecture. Now let's make it very simple. Consider an even nucleus with 2 valence protons and 4 valence neutrons. Think of tellurium 106. So you have 6 particles out of tin 100. So you have 2 protons go from tin to tellurium, and you have 4 neutrons go from tellurium 102 to tellurium 106. So then 2 valence protons make 1 valence proton pair, which means 1 proton boson, and 4 valence neutrons make 2 valence neutron pairs, that means 2 neutron bosons. So you have a nucleus with 3 bosons. And we can make this Hamiltonian even simpler. That's just for pedagogical reasons. So we use these constants here, all 0, and here are also constants in this operator. We put them all to 0. We only keep this term here, okay? So, and then just in order to do a calculation, we put as a neutron d boson energy 1 MeV, proton d boson energy a little bit different, a little bit higher, say 1.3 MeV. Let's look at the spectrum of this Hamiltonian. We can predict it already from well, if I would do it equal, no. It's just to introduce the things. If I make them equal, then something else happens, and this I will discuss later. I just want to do it different. I just take this from the sky. Okay, it's just my choice. So I want to separate the things. So let's look at the solutions for this Hamiltonian. What state will be the ground state? We only have S bosons and D bosons. And we have 3 bosons. If one of them will be a D boson, that will cost energy. If it will be a neutron D boson, it costs 1 MeV energy. If it will be a proton D boson, it costs 1.3 MeV energy. So the lowest energy state will be the state which has no D bosons. That means only S bosons. So we had 2 neutron bosons, 1 proton boson. That means a neutron S boson, a neutron S boson, and a proton S boson. 3 S bosons, angular momentum 0, you can couple them to angular momentum 0 only. Right? So you have a 0 plus state. That's the ground state, the lowest energy state. Now the first excited state you can make is the one where you have, now you must transform 1 S boson into a D boson. A proton D boson is not so good because that costs 1.3 MeV energy. So you first take a neutron D boson. So you have 1 neutron S boson, another neutron, now a neutron D boson, and a proton S boson. Which means angular momentum 0 times angular momentum 2 times angular momentum 0 is angular momentum 2. So you have a 2 plus state. And this 2+ state is a neutron excitation. And that occurs at 1 MeV energy, because you have 1 d boson, 1 MeV. Or you can do a proton d boson, but that costs more energy. So the wave function here is as nu d proton. Right? So this is again a 2+ state, which now occurs at 1.3 MeV excitation energy. I just chose these parameters in order to split them. Then you have 3 bosons. You can have instead also 2 d bosons, which costs more energy, of course. Now it's cheapest if you take 2 neutron d bosons. That costs you 2 MeV in total. And now you have 2 identical bosons that of angular momentum 2 that can couple, that must form a symmetric wave function because they are bosons. So they can couple only to even spins, 0 plus 2 plus 4 plus. So you get this famous 2-phonon triplet, 0 plus 2 plus 4 plus, at excitation energy twice the energy of the first 2+ state. Okay, or you make a higher excitation, you use 1 proton d boson and 1 neutron d boson, and you keep the third as an s boson, which would be a neutron s boson here. So now at 2.3 MeV excitation energy, 1 here, 1 there, you have a new multiplet of states that are formed by a neutron d boson and a proton d boson. But now these bosons are different. And now you can couple them also antisymmetrically because they are different. And you get the full quintuplet of states, 0 plus 1 plus 2 plus 3 plus 4 plus. And there would be a states which I haven't plotted where you have 3 d bosons then. But the important thing is here, so I mean, you can tell already from this Hamiltonian, you know the wave functions, you know the excitation energies, and you know that there appear antisymmetric states with respect to proton-neutron lattice. And now comes your question about the equal d boson energies. Why have done it? I have done this just to introduce this example. Now suppose equal d boson energies. Yeah, you were thinking about Coulomb repulsion and they cost more energies. Well,
I would put them other way around.
Oh, you think the proton d bosons are lower in energy than the neutron d bosons? Is that what you think?
Okay, cool.
Well, it depends so much on the shell structure. Think about these microscopically, they are formed by particles in the shell model, sitting in shell model orbitals. And then you can have different gaps to other shell model orbitals. So you can have different excitation energies for making an S boson into a D boson. They can have different energies for neutrons and protons depending on the underlying shell structure. That can vary through the nuclear charge. So sometimes you can have equal D boson energies, sometimes this can be lower, sometimes that. But these are phenomenological constants that you have to fit to the nuclear region that you want to describe.
Yeah, I look where I am.
And yes, and in principle, yes. But the problem is that doesn't really work that way so well. I mean, accurate enough. I mean, the best way is just to fit a Hamiltonian, to fit the constants to the data of the nucleus you want to describe. Okay, so now we make them equal. That means the proton excitation and the neutron excitation occur at the same energy. And when they occur at the same energy, I have split them up a little bit in order to see the difference. So there's a neutron 2+ state, a proton 2+ state. So any proton-neutron interaction would mix them. Well, that can mix them, of course, so the 2 pluses. And if you mix them, that means they will split up into a symmetric combination and an antisymmetric combination. That's just two-state mixing. Right? So you have psi1 plus psi2 for the lower solution and psi1 minus psi2 for the higher solution. You have discussed the two-state mixing. Okay. And so for exact degeneracy, when you have chosen identical excitation energies of the initial configurations, any p-n interaction leads to this symmetric antisymmetric wave function. And that means you get exact degeneracies of these states for equal parameters in the Hamiltonian for protons and neutrons. So if you use here equal parameters for the proton and neutron d bosons, and here for the quadruple operators, then you get this symmetric and antisymmetric pieces, wave functions. If you have, so then you can consider the bosons also as being identical, only having an internal variable, the isospin label, proton or neutron, that distinguishes these identical bosons. So we can apply here the isospin concept of Heisenberg from the 1930s. So for identical proton-neutron parameters, the proton-neutron bosons are identical particles with an internal distinction, a label. So you can apply this isospin concept, and that reduces, so this is a constraint, of course, to all our possible interacting boson model 2 Hamiltonians. But if we do this, that reduces the complexity of our group structure, u pi 6 times u nu 6, to a spin group times u6 for proton and neutron bosons. So formally, we introduce this boson isospin, like this isospin for nucleons, neutrons and protons. We have a boson isospin of 1/2, where we define the proton bosons to have the projection plus 1/2, and the neutron bosons to have the projection minus 1/2. Okay? And then you can, for a multi-boson wave function, you can couple these isospins to a total boson isospin. And this boson isospin is called F-spin because we use this sign F here. So we do spin 1/2 coupling. So let's look at, think of spin 1/2 objects, two spins 1/2 electrons, and you couple them. So you have the first spin 1/2, the second spin 1/2, and you do product states. You can couple them either to angular momentum 1. Then you have an M substate where the first particle has a spin up, the second particle has a spin up, is M projection plus 1. You can have both pointing down, M projection minus 1. Or you know how to do these ladder operators. You have the first up, the second down, plus the first down, the second up. So this is symmetric under the exchange of the indices 1 or 2. Or you have the antisymmetric combination where you couple them. Well, you know how you must do this. You must have a wave function which is orthogonal to the other state with this angular momentum, with this M substate. So you have this antisymmetric piece with a minus sign here, which only occurs if particle 1 and particle 2 are different. If they are identical, then this is exactly 0. So you get this S equal 1, which is S max. All components contain symmetric coupling of particles 1 and 2. And you get this S equal to S max minus 1, which in this case is 0 here for 2 spin 1/2 particles, which is antisymmetric under the exchange of labels 1 and 2, and which is only non-zero when 1 and 2 are different. Okay, so then you can do, you can form these F-spin operators. I just defined these operators, a raising operator. So remember, proton bosons had an Z projection of the F-spin plus 1/2. Neutron bosons have minus 1/2. So you can increase the Z projection of the F-spin when you transform a neutron boson into a proton boson. Then you have M substate from minus 1/2 to plus 1/2. So an operator that transforms a neutron boson in any quantum state into a proton boson in exactly the same quantum state is a ladder operator for the F-spin. Right? So then you write this, an operator that that transforms a neutron boson into a proton boson in the same quantum state. That means S pi dagger S nu, you annihilate a neutron S boson, create a proton S boson. Or the same for D, you annihilate the Ds in all this substate and create exactly the same substate of the protons. This is the raising operator. The lowering operator is if you do it the opposite. So you annihilate a proton and create a neutron. And in order to have a spin algebra, you have a ladder operator going up, a ladder operator going down, and a Z projection. What is the Z projection for the F spin? Well, you count the number of neutron bosons, multiply it by minus 1/2. You count the number of proton bosons, multiply it by plus 1/2. Then you have the total Z projection of all the bosons. Okay? So that is ND, that is NS. The number of D bosons plus the number of S bosons is the total number of bosons of that type. So you have the total number of proton bosons here. You have the total number of proton bosons there with a minus sign in front. So this is 1/2 n pi minus nu. This is just, you count the difference of neutron bosons and proton bosons. So this is the Z projection. Now, when you can calculate the commutators of these operators, and you find these commutation relations that are exactly the commutation relations of angular momentum operators. So you deal here with a spin. So the F spin operators exhibit spin commutation relations. So that is a group SU2 for F spin, and hence the name F spin. It's like a spin. So a spin has an invariant, right? S square. That is this Casimir operator, which you can write in these ladder operators that I had before. That is a lowering operator times a raising operator plus Z projection times Z projection plus 1. And it has two quantum numbers. So you apply this S square operator to your wave function, then you get S plus 1 times the wave function. You apply the Z projection to the wave function, then you get the M quantum number times the wave function. So these are diagonal in the wave function. And correspondingly, for the F spin, you just produce, that was just a reminder, you know this. And you have these ladder operators also for the F spin, so you form this F square thing, just in analogy to the spin case, so F minus times F plus the Z projection operators, which I had on the previous slide. And then you know that when the wave functions have good F spin, that when you apply this operator, you get F plus 1, and you get the wave functions back. With the boundary conditions, of course, that for the Z projection, that the F spin is always at least as large as the Z projection. Right? The projection can never be larger than the total angular momentum. And the F spin cannot be larger as number of bosons times 1/2, because it can only if you have one sort of bosons, so n proton bosons, you have n times 1/2. That is the maximum F spin you can have for n bosons. So this F spin is always between F max, which is half of the total number of bosons, and 1/2 times the difference of protons and neutrons, bosons. Okay, so now let's look at an example, 2 bosons only. 2 bosons only, and now you can distribute them over proton and neutron labels. So either you have no proton bosons and 2 neutron bosons, then you have the Z projection of the F spin, which was given by 1/2 times n pi minus nu. So 1/2 times 0 minus 2 is minus 1. So Z projection is minus 1. Or you have one proton boson, 1 neutron boson, then Z projection is 0. Or you have 2 proton bosons, but then 0 neutron bosons. So Z projection is 1. So then when you look at the spectra, so here's excitation energy, as we have done this before, you put a simple Hamiltonian and have a 0 plus ground state, and then the 2 plus state, and these sort of things. Then in this case, you can have symmetric couplings only. So for instance, no 1 plus state. But here, when you have different bosons, then you can also have antisymmetric couplings, and new states appear. They appear only in this example because this is the only column where there are different bosons here. So you see, like spin multiplets, these states here have f spin 1, and these new states that appear that contain an antisymmetric piece that can only occur when proton and neutron bosons are available, they have non-maximum f spin. In this case, they are f max minus 1 states because they have only projection 0. So you have f spin 1 states and f spin 0 states, or f max states and f max minus 1. And I'm talking about these states that contain antisymmetric pieces, these mixed symmetry states. Aha, there is mixed symmetry. So f max states, they correspond, of course, to IBM1 because they must be a sort of identical. They contain, they belong to a multiplet where you have states that contain only one sort of bosons, let's say proton bosons only. But when you have only one sort of bosons, you can neglect the label. That is then IBM1. So the f max states, they correspond to exactly to IBM1 states. And if proton and neutron bosons are present, then the wave functions can contain antisymmetric coupling. And you have non-maximum f spin, these purple states. And these are called the mixed symmetry states. Okay, so when is f spin good? You have discussed this yesterday with Professor Joly when these quantum numbers are good. That is when this operator f square commutes with h. And it commutes with h, for instance, when you have equal parameters for protons and neutrons. So you write these operators symmetrically and then give them a common constant. And then you can write this operator that measures the symmetry as f max plus 1 minus f square. For symmetric states, where that means, for symmetric states you have maximum f spin, f max. So then the value of the f square operator is f max plus 1. So then you see that this exactly cancels. So the Majorana operator that I have used before has no effect, has 0 for symmetric states only, and is finite for states that have a smaller value of f spin than f max. Right? So for the mixed symmetry states, it is finite. And if the raising operator commutes also with h, then you have for a certain, you have an eigenstate of the Hamiltonian with some eigenenergy E. Then also the raising operator applied to psi is an eigenstate of h with the same energy, right? Because they commute. And that means that you have in a different nucleus now, because the raising operator transforms a neutron boson into a proton boson. So you go from one nucleus to the other. You have the same energy, so you have isospectral nuclei, because here this eigenvalue stayed the same. So you go from one nucleus, you apply the raising operator, go to another nucleus where you have identical excitation energies. So these are the so-called f-spin multiplets. This is shown here. This is data. This is data for nuclei that have the same number of bosons, 12 in this case, but distributed differently on protons and neutrons. So dysprosium-156, 8 proton bosons, 4 neutron bosons. Erbium-160, 7 proton bosons, 5 neutron bosons, 12 again in total. Ytterbium-164, these are the same nuclei that I have discussed before in this confined Bettasov rotor model. 6,6 Ytterbium-164, 5,7 Hafnium-168, 4,8 Tungsten-172, 3,9 Osmium-176. So it goes all the way to Mercury-184, which is very close already to lead. So there are two. Mercury has Z equal 80. So it's two protons from a closed shell apart, and there you start to see deviations. So what you are supposed to see is that with a very good approximation, I mean, many states have exactly the same energy here. Well, there's something funny going on with the zero pluses, but okay. Now you can say, okay, there are some deviations, so this is not a very good description, but that ranges from mass 156 to at least to 180. Okay, so sort of 24 mass numbers. So if you look, for instance, instead in isobars that are very close, so 162 dysprosium, the neighbor, even 162 erbium, 162 ytterbium, only 3 nuclei, you see much larger deviations. So this is not trivial. I mean, that these F-spin multiplets occur. Okay, so takeaway message 2. The IBM2 Hamiltonians that treat proton and neutron bosons equally, that means it commutes with F square. The eigenstates can be classified by the F-spin, which quantifies the amount of proton-neutron symmetry in the boson wave function. And this F-spin is between F max and Fz. And the lowest states have F max. Okay, now let's consider another simple example. We haven't seen yet the antisymmetry. So now we consider this, yes?
So how these states change? You said IBA2 treats proton equally, but IBA1, I think, positively equally.
Oh yes, yes.
So
But
it's kind of same state.
no, that simply means that the IBM1 is contained in the IBM2 that treats proton and neutron bosons equally. But in the IBM2, additional states occur. And this I will discuss exactly now. So your question was at the right moment. So let's look at this example. You have now the Hamiltonian epsilon ND, where ND means ND proton plus ND neutron. So they are treated equally. They have one parameter in front, the epsilon. Plus at constant times this Majorana interaction, which has only, so we consider two bosons, one proton boson, one neutron boson. So this M can take two values only, 0 for the maximum F-spin and 1 for the non-maximum F-spin. Okay, now let's construct the eigenspectrum. Again, we have a d boson energy term, which costs energy. So the lowest state will have no d boson in it. So S pi S nu. That's a 0 plus state, which is symmetric under exchange of proton-neutron labels. So it's an F max state. So the value of this operator is 0. So that is at 0 energy, ground state. Now we take one d boson. That costs energy epsilon. And it would cost energy lambda if the state would not be symmetric under exchange of proton and neutron labels. So you better make it symmetric in order to have a lower energy. And there's only one way. You have a proton d boson, neutron s boson, plus a proton s boson, neutron d boson. No other way in order to get a symmetric combination. And 1 over square root 2 in order to normalize it properly. So this is the first 2 plus state, which is called quadrupole excitation symmetric, QS. And then you can have the symmetric combinations of proton and neutron d bosons. Remember, when you couple two quadrupole operators, the coupling to even spins is symmetric under exchange. The coupling to odd spins is antisymmetric. So you want to avoid this punishment of this symmetry operator here. So you get the lower energies when you couple them symmetrically. That means to even angular momentum, 0 plus, 2 plus, 4 plus. You could also couple them to odd. You can also couple them to 1 plus, 3 plus, but then they are antisymmetric. Okay, so this is your spectrum for the symmetric states. Ground state, the one quadruple phonon excitation, the 2 quadruple phonon symmetric triplet, symmetric 2 quadruple phonon triplet. Or you do the antisymmetric things. So the orthogonal combination to this symmetric one is that with a minus sign. So you have d proton s neutron minus s proton d neutron. Creation operators acting on the vacuum. Or you have this antisymmetric two quadruple d, two phonon couplings. So you get the 1 plus and 3 plus states. And this is a 1D boson state, so it's a 1 phonon excitation, which has this minus sign here, so it's an antisymmetric quadruple excitation. If you have more than 2, then you see that it only contains antisymmetric pieces, so it has some mixed symmetry, and therefore it's called the mixed symmetry excitation. So this is the mixed symmetry quadruple phonon excitation, that is a symmetric quadruple phonon excitation. And on top of that, you can do 2 phonon states with 2 d bosons here, and you have a 1 plus and 3 plus states. If you have more than 2 bosons, you would have here the full quintuplet of states, 0 plus, 1 plus, 2 plus, 3 plus, 4 plus. Okay, so now you have seen what comes in addition from IBM 1. In IBM 1, you get only these states. So these states, these are the mixed symmetry states. They contain antisymmetric pieces, and they are new states that only appear in IBM 2. Okay? Although you have the Hamiltonian, you have equal parameters for protons and neutrons. But the space is richer. Yeah, and the breaking, so yes, so they appear at, so this is the 1D boson state, so you have ND is 1, so you have the excitation energy epsilon, plus they are mixed symmetry, so F max minus 1, then the value of this operator is 1, so you have lambda. So they occur at energy lambda plus epsilon. This occurred at epsilon, this at lambda at epsilon. I say lambda is here 1.7 or so. Then these states are shifted to here, and this is 1 MeV higher. So new states appear that have a minus sign in the wave function. So we have discussed so far the U5 limit in this F-spin limit of the SD IBM2. So where the F square operator commutes with F. That is restriction. And then these groups U nu 6, so neutron U6 times proton U6 reduces to a proton neutron 6 and a proton, and then you can have the U5 chain U5, O5, O3. So in that limit, you can diagonalize the Hamiltonian, you can write it as a series of Casimir operators that occur in this chain that you have discussed at length yesterday in the lecture of Professor Joly, and you obtain an analytic solution that have these constants in here, and quantum numbers here occur, 2 quantum numbers for the d bosons and 1 and 2 that are related to the F spin. And this is the Majorana operator, as you can write it here. So the message is there is an analytic solution with an energy formula in terms of these quantum numbers, and this is from the Van Isacker review, this figure. So you have this ground state, the symmetric quadruple excitation, the symmetric 2 phonon triplet, 3 phonon states, and then these are all symmetric states, and then come the mixed symmetry states. There are only a part of them, right? There will be more symmetric states depending on the number of bosons that you have, and there will be more mixed symmetry states, but they are only the lowest ones. So you have the 1 quadruple phonon excitation, the mixed symmetry, and then you have this full quintuplet of states, 0 plus 1 plus 2 plus 3 plus 4 plus, and they are split somehow with an L square term. So with this term, they are split up such that you can better distinguish them. And also, in the other two in the dynamical symmetry limits of the interacting boson model 1, you get solutions in the interacting boson model 2 in the F-spin limit, which is then the SU3 limit for the rotors and the O6 limit for the gamma soft nuclei. This I will not discuss so much here, but the rotors, you see that all these excited states, they form bands that we have discussed this morning also in the context of the confined Bether-Soft rotor model. But there appear mixed symmetry states with the lowest band that is a k equal 1 band. A k equal 1 band does not occur in the IBM1 as the IBM1, but it occurs in the IBM2, and that has historically a quite important role because this band head is a 1+ state that was the first experimental example of a mixed symmetry state, which I will show you later. Okay, so the third takeaway message is, so we have discussed the Hamiltonian for the IBM, we have discussed F-spin. The F-spin limit of the IBM2 has 3 analytic solutions. They correspond to the IBM1, so to the analytic solution of the IBM1 U5 limit, O6 limit, SU3 limit. But in contrast to the IBM1, new states appear, those with non-maximum F-spin, the mixed symmetry states. Other questions? Okay. So how do we find them experimentally? I mean, we can try to measure our levels and then fit the Hamiltonian parameters to the level scheme, and then try to look for extra states and then identify them with a mixed symmetry state. But then we cannot really be sure if these were the right states. We need more. We need unique signatures for these states in order to identify them experimentally from the many, many excitations of a nucleus. The experimental signature for mixed symmetry states are magnetic dipole transitions. We haven't discussed M1 transitions before because they are not very well described in the IBM1. So the M1 transition operator is, well, maybe there's one step missing here. The magnetic dipole has angular momentum 1. So the only operator that produces angular momentum 1, which contains a boson creation and annihilation operator, is in the IBM is d dagger d coupled to 1. D dagger d coupled to 1, which is proportional to the angular momentum operator. Now you can have this for protons, then you have the angular momentum operator for protons, or you can have it for neutrons. And the M1 transition operator, do we have something? Aha. The M1 transition operator must be constructed out of angular momentum 1 operators in the IBM1. So Tm1 is equal to the proton angular momentum operator times a G factor, an effective charge if you want, plus a neutron angular momentum operator times an effective charge. And the total angular momentum operator, L, which is a good quantum number for all states, is the sum of the proton and the neutron angular momentum operator. Since all states have a good angular momentum, this operator is diagonal in all states, so it cannot produce transitions. So then you can write this operator in terms of the sum and the difference. The sum is the total. That cannot make a transition, and the difference is here. So you have then the difference of proton-neutron G factors in front, and some constants which we can neglect here, and you have the difference of proton and neutron angular momentum operators. How does this operator act on the mixed symmetry state? So remember, for the two bosons that we have the wave function of the mixed symmetry quadrupole phonon excitation. So we have S dagger nu d dagger pi minus S dagger pi d dagger nu. And now this operator acts on it. So this piece transforms a d boson proton into a d boson proton. So it connects this piece to that piece of the first 2+ state. And here's a minus sign, and this piece transforms a neutron d boson into a neutron d boson again, but it changes the sign of this term, so it produces this plus sign here. and the total angular momentum cannot contribute to M1 transitions. So the M1 transition operator transforms the mixed symmetry state into the symmetric quadrupole phonon excitation, which means there is a strong allowed matrix element between these states. So you have large M1 transitions between a mixed symmetry state and a symmetric state. Or in other words, M1 transitions are of isovector nature, and it changes the isospin of these boson wave function, the F spin. Right? And usually, I mean, you take pure orbital values of the G factors. That means for protons you have 1, for neutrons they are uncharged, you have 0 nuclear magneton. So then G pi minus G nu is about 1 mu n times some constants in front which are of the order of 1. Then you expect matrix element between M1 matrix elements between mixed symmetry states F max minus 1, F spin F max minus 1, and F spin F max of the order of 1 nuclear magneton. So, and these are very large M1 matrix elements. Typically, M1 transitions between symmetric states are of the order of 10 to the minus 2, 10 to the minus 3 mu n square between the low energy states in the level scheme. I mean, those that we have discussed this morning. Yeah, Jan?
Just one remark, it was a question in the formula you are missing K plus K.
Here?
Yeah.
Yeah. Okay, so this unique signature for the mixed symmetry states, at least in the vibrator limit, is there must be a 2 plus state, which is a 1 phonon state, but antisymmetric. So where protons and neutrons have opposite signs here in the wave function. There will be a strong M1 transition to the symmetric first 2 plus state with the matrix element of the order of 1 nuclear magneton. And an E2 transition, which is, at least it's a 1 phonon state, but protons and neutrons work in opposite directions, so it's a sort of reduced, so it's not so collective as here, but has some collectivity, let's say a Weisskopf unit or so. And then, so this was the 1 phonon to 1 phonon transition. You can have higher phonon states, as we have discussed previously. So this is QSQM. If you have 2 bosons only, there is a 1 plus 3 plus state. Now you can transform the mixed symmetry quadrupole phonon into a symmetric quadrupole phonon. Then you end up from this 2 phonon state. You replace this by QS. You end up in the 2 phonon states. So you expect also strong M1 matrix elements from the higher multiplets to the higher multiplets here. Mixed symmetry to symmetric. Right? Okay. Why is that M1 transition actually a good signature? I said before all the others are small, but why is that so? You can find the reason in the review article of Professor Isaker. You can write the M1 operator also a little bit different. Here is it, so here you see also this analytical factor, square root of 3 over 4 pi. G pi L pi plus G nu L nu in nuclear magnetons. So you can write that as the sum L total is L pi plus L nu, but in a more fancy way, where back here you write it as L pi over N pi minus L nu over N nu. And this equality holds. I mean, you can check it. So the total the total angular momentum operator is diagonal, cannot make a transition, right? So we can forget about this piece when we discuss transitions. Now you are left with this piece here that is able to produce transitions between states. That was, so we can forget about this thing. But now let us consider only symmetric states, the IBM1 states. So not those that have the mixed symmetry character, only the symmetric ones. Then there is a relation that if you have an operator, a 1 boson operator, so B dagger B, so 1 annihilator, 1 creator, between symmetric states, those that have F max, independent of all the other quantum numbers, then this will be a certain constant, which depends on the other quantum numbers, times the number of bosons of this type that you have. So this is just proportional to the number of bosons that you have of this type. Which means that when you plug this operator between symmetric states, so Fmax states, then the L pi operator put here, that is d dagger pi d pi, produces a constant times n pi. And this L nu produces the same constant times n nu. So that means there is a constant n pi over n pi minus the same constant n nu over n nu. So the constant goes out, and then you have 1 minus 1 is 0. So also this piece back there is 0 when it comes to M1 transitions between symmetric states. So that is the proof that in the IBM1, M1 transitions are forbidden between symmetric states. On the other hand side, we said mixed symmetry states produce very large M1 transitions. So M1 transitions are a unique signature to find the mixed symmetry states. Okay, because they are forbidden between symmetric states. Aha, no M1 transitions between full symmetry states, occurrence of sizable M1 matrix element of the order of 1 nuclear magneton, a strong signature for mixed symmetry states. So that is the takeaway message 4. M1 transitions with matrix elements of the order of 1 nuclear magneton in size are unique signatures for mixed symmetry states. Okay, there were trials before to find these mixed symmetry states by not measuring the absolute M1. That is quite difficult. But to look at E2 to M1 multiple mixing ratios, so intensities that goes by E2 divided by intensity that goes by M1, and if you have small values, then you hope that maybe that means that the M1 is large. But that is not always unique. It's better to look directly, absolutely at the absolute M1 matrix element, which is, however, difficult. Well, I don't discuss this detail. So one way to excite these 2 plus states, the one phonon mixed symmetry state in a vibrator, is to shine with photons on them, with gamma rays. You excite that level, and the cross-section for exciting the level with photons is proportional to the BE2 of the ground state. If you know the branching ratio and the E2 to M1 multiple mixing ratio for the transition to the first 2 plus state, then you can get an absolute M1 matrix element out. And that was an example of Bari 136, where we did this for the first time in photon scattering. You have several 2 plus states in Bari 136, but there's one 2 plus state at 2.2 MeV, which has a large M1 matrix element. The BM1 value is 0.25, and that means the M1 matrix element is 1.1 nuclear magnetons. Because maybe you are not all aware of the fact that the B pi lambda from an initial state to a final state is 1 over 2j initial plus 1 times the square of the pi lambda matrix element. So if BM1 is 0.2, or if the matrix element is 1 nuclear magneton, in square is still 1 nuclear magneton square, divide by 2 times 2 plus 1, so it's divided by 5. That means 0.2 mu n square would be the BM1 value if the matrix element is 1 nuclear magneton. And that is what we have seen there. The same method, photon scattering, also excites 1 plus states. So with this method, one can identify both the 1 plus mixed symmetry state and the 2 plus mixed symmetry state. So the height of the peaks is proportional to the cross section from the ground state. And if you know the decay path, you can tell the M1 transition rates, and you can identify these states as mixed symmetry states. The interesting point here is there was also a gamma ray spectroscopy study of molybdenum-94, where one gets a direct transition between the mixed symmetry states, the 1 plus mixed symmetry state here to the 2 plus mixed symmetry state. in a coincidence gate on the decay of the mixed symmetry 2+ state. That is this transition here. So that was the proof of the fact that these structures, the mixed symmetry states, they form a class of states with the same structure. So molybdenum-94 was investigated extensively with respect to these low spin states, and that is a part of the level scheme, where blue means strong M1 transition, and the blue numbers give you the M1 matrix elements. They are measured. And green means E2 transitions, collective E2 transitions between states with the same F spin. And red means E2 transitions with between states with different F spin. So you see this bottom part of this phonon structure of molybdenum-94. So it has 52 neutrons. So it's 1 neutron boson away from the n = 50 shell closure. So it's a vibrator. With the first 2+ state with an energy 871 keV, close to 1 MeV, and the 2 phonon states somewhat close to twice this energy with some splitting. And then there's a third 2+ state here, which has a strong M1 matrix element to the first 2+, 1.7 nuclear magnetons. And there are 1+ and 3+ states on top that have strong M1 transitions, not to here, but to the symmetric 2 phonon states. So 2 phonon to 2 phonon. The 1+ can decay only to the 2+2 here, and the 3+ by M1. M1 can change spin only by 1 unit of H bar. So the 3+ can decay to the 2+2 and to the 4+1. And also these M1 matrix elements are large, 1.2 nuclear magnetons for this transition and 0.7 nuclear magnetons for the first 4+. And there are transitions that I have shown you before the evidence. There are transitions from these states to the state, so from the 2 phonon states here to the 1 phonon state there. That corresponds to the annihilation of a symmetric quadruple phonon. So should in principle be as collective as this one, so 16 Weisskopf units. But, well, we don't have it so nicely. We only have limits. So the 3+ mixed symmetry to the 2+, so 2 phonon to 1 phonon is larger than 1 Weisskopf unit and smaller than 72. So okay. At least it's consistent. It's not inconsistent to this strong collective E2, and there's a limit for the 1+ to 2+ mixed symmetry. It's larger than 3 and smaller than 27. Okay, now you can ask the question, are there more states that look like this? So do we confuse ourselves, or is that trivial? There are many states that have this property. No. If you want to find this out, you have to measure all 2+ states. You have to measure all the M1 matrix elements in the decays to the first 2+, which means you have to measure the lifetimes, the complete decay scheme. You have to know the multipolarity of the transitions, E2 or M1. You have to measure them all. And that takes a lot of time, but can be done, but only in few cases, right, in order to demonstrate that these things are real. So therefore, I mean, this is available for molybdenum-94. So we have measured the BM1 strengths from the excited 2+ states up to the 8th 2+ at about 3.5 MeV to the first 2+ state, and there's only one, only the third 2+ state, which has a large M1 transition to the first 2+. So this is the unique mixed symmetry 2+ state. And this is the BE2 excitation strength from the ground state to all these 2+. And this is on a log scale. So this is dominated by the symmetric 1 phonon excitation, the first 2+, of course. But the mixed symmetry state is also 1 phonon excitation, and it has also a large, here the second large E2 excitation strength of the order of a few Weisskopf units, 2 Weisskopf units actually. Okay. If you want to identify the 2 phonon states, you have to do exactly the same also for the higher spin states, or for the other spin states. So you have to measure the M1 strength distribution from all the excited states to the, let's say, to the second 2+ state here, which is a 2 phonon state, which again is a lot of work. We have not so many data here for 1 pluses. But the first fact is you observe states that have large M1 matrix elements. So this is 0.3, 0.3, 0.3 mu n square for this going up in order to have always the same spin factor in front here. There was where is it? Here, there's a 1 over 2j plus 1. So since these final spins, they differ, I have plotted it in such a way that it always starts from the same state. So this is always the same constant here. So you find M1 transition strengths that are always 0.3 mu n squared. So they all have the same M1 matrix element. So that already indicates that they have the same structure. They all occur at 3 MeV. And there are other states that have much smaller M1 strengths to the second 2 plus state than these states here. So you can identify these states as the 2 phonon mixed symmetry states in that way. Okay. So I have discussed this already. So now we have identified the 1 plus and 3 plus states up there as 2 phonon mixed symmetry states from the M1 transition to the symmetric 2 phonon states. And you want to know if they are really connected, if they really form an entire class of states with the same f-spin quantum number. And that was this observation of this transition between the mixed symmetry states of 2 phonon and 1 phonon character. Okay, well, we have discussed this already. So takeaway message 5. Mixed symmetry states have been identified to form an entire class of states from the measurement of absolute M1 transitions. And the best known example for the vibrational mixed symmetry states is given by the level scheme of molybdenum 94. Now, I've discussed already photon scattering. An experimental method that was used recently strongly to investigate these mixed symmetries, the 1 phonon mixed symmetry states, was Coulomb excitation. And therefore, I want to show this method, how this works to you, and how one can identify the mixed symmetry states there in these reactions. So Coulomb excitation means you excite a nucleus by another ion that passes this nucleus, but they wouldn't touch. They do not interact by the strong force. They just interact by the Coulomb force, because there is a fast passing charge that produces exchange of virtual photons. So you can excite the nucleus when it absorbs them, and it will excite predominantly 2 plus states. We want to look for 2 plus states. And the E2 excitation strength is proportional to the cross-section that you can measure. So you can measure how often you have excited that nucleus to that particular state, and you have the cross-section, and then you know the E2 excitation strength, which means when you know the decay pattern, you know its lifetime. Traditionally, you do this with light ions on a heavy target when you want to investigate a heavy nucleus, but if you do you can also do projectile Coulomb excitation. So you turn this around, you shoot with a heavy nucleus that you want to investigate on a light target, and you excite the heavy nucleus. Then this is called projectile Coulomb excitation, because a projectile is the nucleus of interest. And then you can look at the gamma rays that come out of this nucleus with a large detector array for gamma rays, and you can measure gamma ray angular distributions and gamma intensities, of course. So from the gamma ray angular distributions, you get the multipolarities. You need to know them because you want to extract also E2 to M1 multiple mixing ratios, because you want to measure finally an M1 transition strength. And you can measure spin quantum numbers, so you can make sure that you see 2 plus states, or that you can distinguish the 2 plus states from 3 minus states or 4 plus states. And from the gamma intensity, you get the gamma decay branching ratios out. You get out how often the level was populated. The more it was populated, the higher is your intensity for the decay that you observe. That means you get then from the total population, from the total reaction yield to get the excitation cross-section, and from the excitation cross-section with all this information, you get then the absolute lifetimes and the absolute transition rates. So everything what you need. Yeah?
Just a question. You described that we have two ways of doing either direct kinematic or inverse kinematic.
Yes?
Maybe I missed it, but why would you be interested in inverse kinematic? Because of course you will have to take into account the Doppler effect. That's going to
Right. Yes.
be, like for
This is much more complicated than this one. So people have mostly used this technique. And also the resolution is better, so it sounds like really stupid doing it this way. Now the funny thing is, so when you shoot a light, here I have the example of cerium-138. Let's suppose you want to populate low spin states, so you want to have a light particle and a large particle, because you don't want to have too much multi-Coulomb excitation. So if you shoot, let's say, carbon on a heavy nucleus like cerium, close to the Coulomb barrier, you are for sure above the Coulomb barrier for carbon on oxygen, carbon on iron, carbon on aluminum. So that means that you are above the Coulomb barrier for every material that is in your experiment. I mean, your target chamber is made out of aluminum or out of steel, so you scatter particles and you produce reactions there. So that means you have a lot of background, and that does not allow you to measure the Coulomb excitation in gamma ray singles. Or in singles, you are only sensitive to the Euras bands. You see them very strongly, but you need singles because you have to identify the transition to the ground state in order to observe the one-phonon states. If you do it inverse, and you must make sure that you are with a heavy particle below the Coulomb barrier on carbon, then you are for sure below the Coulomb barrier to everything else in the experimental setup, because there is no boron, lithium, and so in your setup, and beryllium. So that produces very, very clean spectra. Or you can use gamma ray singles, which you anyways have to take in order to measure the transitions to the ground state. And the gamma ray singles allow you to use an enormous count rate such that you see also very weak population branches. And this was actually the trick of this approach. So you come with your heavy nucleus, scatter it on carbon, you Coulomb excite it. It will de-excite, so I mean, you hope that you have excited it to its 2+ mixed symmetry state. It will either de-excite by an E2 transition to the ground state, or it de-excites by the M1 transition to the first 2+, which you have to measure. I mean, the E2 to M1 multiple mixing ratio and the decay transition rate. And then that decays to the ground state also, and you measure these gamma rays by your detector array. And here comes the point. So we did this you need a big accelerator. So you are talking about half a GeV of energy for these ions to come close to the Coulomb barrier. So you see cerium-138 at 480 MeV. That was done at Argonne National Laboratory near Chicago. This is singles in this gamma sphere detector array. And here you see the count rates. That is the first 2+ state. Here's the log scale. The first 2+ state, there are several channels wide, and the count rate here is several millions per channel. So you have an enormous count rate. That means you have an enormous sensitivity. And what we are interested in is these structures here. So that is at least still like a couple of thousand counts per channel. This one is the E2 decay to the ground state of the 2+ mixed symmetry state, and that is the M1 transition, here, this one here in the middle, the M1 transition to the first 2+ state. And this is only possible because we can count so fast and we can use gamma ray singles. And this is possible because we are inverse and we have no nuclear reactions. And this is now also applicable to exotic nuclei, because exotic nuclei, in radioactive beams, you can use them in order to do this projectile Coulomb excitation, but you cannot make a target out of it. So you can do these at this radioactive beam facility. So that was done at Argonne with the Atlas superconducting LINAC, so heavy ions with to 80% of the Coulomb barrier using the gamma sphere detector array, 100 germanium detectors shielded with, from Compton scattering events with anti-Compton shields. And we have done a series of experiments in order to extract the M1 transition strengths. Now I show you how this works. So in this case, we observed all 2+ states up to 2.7 MeV. So we expect this 2+ mixed symmetry state to be located at around 2 MeV. But we have to measure them all. We have to identify them all and measure the M1 transition strengths to the first 2+ states. So that is the single spectra. But of course, you also have coincidences with these big detector arrays. And that one is the 2+ mixed symmetry state, which I will show you now. So first, you have to identify spin quantum numbers and E2 to M1 multiple mixing ratios. So you do this by angular distributions. So the angular distribution function, so you have an initial state J, I, a final state J, F, an E2 to M1 multiple mixing ratio, and the observation angle theta. And then you can, by this angular momentum theory, you can decompose this into orientation coefficient, into some parameters that depend on this on the spin quantum numbers and the multipolarity of the transition and the Legendre polynomials. So let's consider the mixed symmetry state. So that is the 2+ state at 2.237 MeV. So from the ground state transition, we observe an angular distribution from which we obtain these asymmetry parameters A2 and A4 that occurred previously in this formula for the multiple for the angular distribution, and we can tell that this is a quadrupole transition. From this distribution, angular distribution, we get the A2 and A4 coefficients, which gives us the alignment of the states. So that is the probability for the M substate population. It's a 2+ states, so it has M substates from -2 to +2. They lie on such a Gaussian. So here you see the data points. Now we know the M substate distribution. And we observe also the transition from that state to the first 2+ state, of which we want to measure the E2 to M1 multiple mixing ratio. But now we know already the M substate distribution. So this we can plug into an expected angular distribution coefficient plot as a function of A2 and A4, these asymmetry parameters. For this M substate distribution must be this curve as a function of the E2 to M1 multiple mixing ratio. So here is pure M1, here is pure E2, and in between that is mixed, and that is what we measure. Yeah, so this is the best value is a very small E2 to M1 multiple mixing ratio, 0.1 something here. It's 0.18. So that means that is 97% M1 transition strength. So first we have measured now the E2 to M1 multiple mixing ratio and the spin quantum number. Then from this from the gamma ray intensities, we get the population cross sections. We get the yields. So we normalize everything to the first 2+ state, which has a known lifetime. So the first 2+ state is 1. The second 2+ is populated at a level of 1%. This 2+ state here, that is of interesting, is populated to a level of a few per mil. And there are other 2+ states for which we can do this sort of analysis. Now we know that the BE2 excitation strength of that state, and we can do a Coulomb calculation with a code for this multiple Coulomb problem, and then we get the B sigma lambdas for all the transitions out. And from the branching ratios, we have the lifetimes. And that results in these lifetimes. So we have the first 2+ state, second, third, fourth, fifth, sixth. We have all these lifetimes. And we get the E2 to M1 multiple mixing ratios out from the angular distributions. And then we get the M1 transition rates. This is for a neighboring nucleus, cerium 134. That is a plot of the same experiment. And here, a distribution of M1 strengths to the first 2 plus as a function of energy from 500 to 2.5. And there's one state here which sticks out, which has a large M1 transition rate of 0.3 mu n squared. So this is the 2 plus mixed symmetry state in that nucleus. And the same happened in cerium-138. So we have done this at Atlas on a couple of stable nuclei in the mass range about 130, so xenon, barium, cerium, samarium nuclei. And that came out of this series of experiments. So a distribution of M1 transitions from excited 2 plus states to the first 2 plus states. And here that is n equal 80. So n equal 82 would be next. At n equal 82, you have a neutron shell closure. So no neutron bosons, which means no mixed symmetry states. Right? So therefore, n equal 82 is not shown. It starts from n equal 80, n equal 78, 76, 74, and so on. So if you have, so close to the shell closure, you have good vibrators. You always find this one strong M1 transition. Here it is fragmented into 2. There is a discussion why it is so. Most likely that is related to the fact that at cerium, 58 protons, you are at a situation where the G7 half above Z equal 50 is closed, and that produces a fragmentation. So you cannot, in the valence shell for protons, you have 8 protons in the G7 half, it's full, and then you cannot make a D. So you have to lift the particles to a higher excitation, and that produces then this fragmentation. Well, at least there's some M1 strength there, but here's very well developed mixed symmetry state. And then when you go towards mid-shell, you start to deform the nuclei. So here's a sort of the phase transition to deformation. This M1 strength decreases, and we cannot find it anymore here, which was unexpected, though. We expected that it would stay everywhere. I mean, this is still under debate. Maybe it shifts to higher energy and it escapes our observation. I mean, that could be, yeah?
You said you couldn't find it. It means it's a lower limit, right? I mean, you have error about the fact that you do not find.
Oh, yeah. First of all, well, it could be more fragmented, that all the fragments have M1 strength that is below our detection limit, which, however, would mean that this state has dissolved. I mean, it disappeared. Or I said we were sensitive to all 2 plus states up to 2.5 or 2.7 MeV. Now, if that state is shifted to higher energy, we are not sensitive to it anymore. Right? So maybe both, it fragments and shifts to higher energy, as it should actually, then it would escape our detection, and therefore this spot is empty.
Look at the, I mean, the energy is not changing, just the cross section is changing. If it's shifting to high energy, do you think it would shift like immediately? Because look, the energy of the M1s.
2 MeV, here's already 2.2. Yeah.
Yeah,
Well,
but it stands about from a little bit below 2 and a little bit above 2. So you cannot suddenly go from.
Yeah. But
Yeah.
but in these deformed nuclei, the experiment is more difficult because the first 2 plus is lower lying. It sucks much more cross section, so we count much more. We have a limit on the count rate that we can afford in the experiment, so we have to reduce the intensity, so we are less sensitive. So in these nuclei, we are sensitive to 2 plus states only up to 2.2 MeV. For that reason, and 2.2 is exactly the energy where it is already here. So. I mean, that is not unlikely that we have missed it. Jan?
Could it not be that the 1 plus comes below the 2 plus?
Not here yet.
Not yet.
Because they are not SU3, they are more like between, the xenons are between U5 and O6. So you have a sort of O5 pattern, and then there's a 2 plus tau equal 1, and the tau 1, tau 2, 1, 1 states above them.
As far as I know, but maybe you know better, on top of the 1 plus in the form quickly, never the 2 plus has been.
Oh yeah, but that is a transition. This has never been observed, is correct, apart from a person who is in this room, which is Herr Beck. Maybe he has first indication of the 2 plus state in the scissors band. And Achim Richter claims that in '84 he has seen it, but this is wrong. Because no, we can prove that this is wrong because Herr Beck has the data.
Did you ever try a semi-magic nucleus to see that you don't see the nucleus in M1 state?
Yes, we have a beautiful data set on xenon 136 because we wanted to do alpha transfer on carbon to radioactive barium 140 in order to see this mixed symmetry state there. There was a theory with Vituri, but it didn't work. But we have a very nice data set on xenon 136. First 10 2+ or so with all the lifetimes. It's not yet finished. I mean, my student Christian Stahl is working on that. That will come soon. So and I don't think there's strong M1 up to 3 MeV or so. Okay. Then you have seen here in this corner there's something missing. I mean, you have this nice this evolution of this M1 strings. Stable nucleus, xenon 134 is stable, and then there's tellurium 132, which is neutron-rich, unstable. And I said we can do this technique also with radioactive beams. So this was done at Oak Ridge. Miroslav Danchev has taken data for some different reason. And there is a 2+ state at some energy here. I forgot that you have to add these values. And then there is an expected 691 keV transition, which would be the strong M1. And this state was seen in Coulomb excitation. Unfortunately, the branching ratio is not very well known. It has a very large error bar, which means that we get the BM1 value only as a lower limit, but it's larger than 0.2 mu n squared. So it's clear that this is a mixed symmetry state. So that now makes this systematics a little bit nicer. So I mean, this is shifting to lower values. So the mixed symmetry state is here already at 1.6 MeV in tellurium 132. So this is the first application of this method for the mixed symmetry states to radioactive nuclei. And you see now this splitting from the proton-neutron interaction. What you see here is the energies of the first 2+ states as a function of proton numbers in the n = 80 isotones. So this is tin 130, tellurium 132, xenon 134, barium 136, cerium 138. And so the first 2+ states are known here. So they decrease. The larger you make the valence space, the more collective become the first 2+ states, and it goes lower in energy. And here you have seen, here you see the mixed symmetry states from tellurium, radioactive, and then xenon 134. And so you see this splitting. The larger you make the valence space, the larger becomes the proton-neutron interaction, the more does the symmetric and the antisymmetric state split. So you can measure locally the proton-neutron interaction in the valence shell if you want. Okay. Takeaway message 5, Coulomb excitation is a great method to study the 2+1 mixed symmetry state. So the one phonon mixed symmetry state, at least in vibrational nuclei. There was a question with the 1+, the 2+ on top of the 1+. We have also tried to do this when we go to deformed. So we did samarium 154, but that was too difficult because the first 2+ state is already so low, has a very large intensity. And we weren't sensitive enough. That's very difficult. Okay, now in the last 2 minutes, I want to convince you on the fact that this antisymmetry actually can be measured directly. That is the defining characteristics of this mixed symmetry state, that there's a minus sign here between proton and neutron parts. If there are more than 2 bosons, it is only in one piece of the wave function, but there are some antisymmetric pieces. But this seems to be impossible to measure, but there are some evidences that prove this or that support this antisymmetry. So if you want to be sensitive to proton pieces and to neutron pieces independently, what can you do? You can study the protons by charge, by Coulomb excitation, or by electron scattering. Electrons are only sensitive to the protons. And you can study the mass by hadronic reactions, so do proton scattering. So let's compare electron scattering and proton scattering. And let's do it on molybdenum 94 or zirconium 92, which is very close. So you need an electron accelerator if you want to do the electron scattering experiment. We have it in-house. We have this superconducting Darmstadt linear accelerator, which is a 130 MeV machine. In principle, we can do 70 MeV, 100 MeV gamma electron beams. Well, that is a photograph. I skipped this. We have done electron scattering on molybdenum 94, where we know exactly where the mixed symmetry states are. And surprisingly enough, that's a very large signal. So this is an elastic line that is the ground state, electron scattering on the ground state, electron scattering on the first 2 plus at 70 MeV, first 3 minus, and this one is the third 2 plus, the mixed symmetry state. It's very large. Well, of course it's large because it's a one-phonon state. Electron scattering populates predominantly one-phonon states, right? Because electrons are relativistic. They just exchange one virtual photon, you excite a state, and then you have the one-phonon states. And we see many other 2 plus states up to the 11th 2 plus states. And then we compare this electron scattering to proton scattering. Also proton scattering, that was done at 200 MeV, produces sort of the same spectrum, same resolution though, 30 keV about, first 2 plus, mixed symmetry 2 plus, first 3 minus, and then many other 2 plus states. And now, my time is up, but so here you see that is now same data on zirconium 92. We also know what the mixed symmetry state is. The point is, here you see the diffraction pattern, cross-section proton scattering, cross-section electron scattering as a function of momentum transfer. And you see in proton scattering, you see this shift in transition radii systematically. The transition radii shift to smaller momentum transfers for the full symmetry state than the mixed symmetry state. So the mixed symmetry state has a smaller transition radius, because then the diffraction pattern are expanded. And in the electron scattering data that are sensitive to the protons, you see that this is independent of the momentum transfer, which means they have the same, I mean both states, that is now the ratio, they have the same transition radius for the charge, the same proton transition radius. So from these experiments we know that the meta transition radius for the 2 plus mixed symmetry state is smaller than the meta transition radius for the first 2 plus state. But we know that the charge transition radius, they are equal. And we also know that the valence neutrons, they are sitting in the 2d5 half orbitals with a node, have a larger radius than the valence protons in the 1g9 half without a node. And that means then that the neutron component flips its phase. If I would have had time, I would have made the argument, but I want to show you just the composition. So the 2 plus states of neutron excitation and proton excitation in the valence shell, they split up by the proton-neutron interaction into a collective piece, which you can obtain from the coupling of higher resonances, and a valence shell excitation, where the neutron component changes its phase in this situation. And that was the one where the neutrons have a larger radius in the valence shell because they are sitting in the 2d5 half orbital. And now you can plot the contributions to these wave functions to the transition radius or to the density of the levels. So the collective piece is equal for the symmetric 2 plus state and the mixed symmetry 2 plus state. The neutron piece adds to this in the symmetric state. So here it has a node, 2d5 half. So it has a larger has a contribution at larger radii. But in the mixed symmetry state, there's a minus sign, so you subtract contribution at larger radii for neutrons. And that means you change the average location. So this is when you sum the collective piece and the neutron piece for the symmetric state, you end up here on average. And when you sum these contributions up with the opposite sign, you end up at smaller transition radius for the mixed symmetry state. That means the different neutron transition radii are the consequence of the mixed symmetry character of the minus sign. So these patterns, that is experimentally observed, also systematically, in molybdenum 94, zirconium 92, you see a systematic decrease of the transition radii for the mixed symmetry state for these cases where the neutron valence shell component has a larger radius because it has a node. And that means in these cases, the quantum mechanical phases have been accessible. Okay, I'm at the end for this lecture. And I thank you very much, and you can ask questions. Or we go for lunch.